Okay. And we said that there is a connection between these two which we established by means of modeling. And the list of physics parameters can be different for each of us. The list of observers can also be different for each of us. We have studied the global signal, the 21 centimeter forest signal. Prasoon has mentioned the fluctuating 21 centimeter signal. Okay, and then there is this other reverse arrow which is very important, which is in some sense that is why we do all this thing, and that is inference, which I will unfortunately not have time to discuss, but hopefully some of you could study separately. Okay, so this was the context behind the lectures, and then we had gone on to define our basic quantity against the brightness, temperature, TB, its relationship with some of these physics parameters. So we said that our observable would be this TB, and we said that we had its connection with XH1, with the gas density delta, with the liquid velocity parallel, and with the state temperature. Okay, and this relationship is between this side and that side is what constitutes modeling, and we had started sort of fleshing out the relationship between the TB and the TSS. So we wrote down this connection, and we had written expressions for the collisional coupling coefficient and the kinetic temperature, which decides the strength of the collisions. And then we had started talking about X alpha and T alpha, also written as TC sometimes, right? Which is the Lyman alpha coupling coefficient, the Wauthausen field effect coupling coefficient, and the temperature which defines the strength. So we had in yesterday's lecture discussed these, and this we had just started. And I had commented that since then Kanan has described this very nicely in his lectures as well. But then what I wanted to do was to continue my discussion of the Lyman alpha coupling yesterday and to highlight some of the subtleties beyond the very important canonical treatment that Kanan has discussed. And so this, we said yesterday, is related to the intensity of the Lyman alpha photons or the UV photons J alpha. Okay. We said yesterday that now the job is to calculate J alpha, and the J alphas would be related to the sources that produce Lyman alpha photons. Under normal astrophysics, you would typically use galaxies and stars, but you could have exotic models where other sources. And so the problem, however, is that in a naive way of calculating J alpha, what one would do is one would just calculate how many sources of Lyman alpha exist in a univolume of the universe and how bright each source is, and combine everything. But what happens actually is that calculation misses the fact that some of the Lyman alpha photons are eaten up by the hydrogen atom, right? Simply because of this coupling. As a result, the correct calculation actually involves sort of a dynamical equilibrium calculation between the production and the absorption of Lyman alpha. And that is the hard bit. That calculation is not so easy. We often just neglect it, and we do the simpler version of the calculation, where we just calculate J alpha, and we just ignore that J alpha distorts because of absorption by hydrogen. But this ignoring of this distortion is inconsistent, because of course there are, otherwise this did not exist at all. Now, so the goal now is to calculate J alpha in the presence of these interactions with hydrogen. Okay. Now, yesterday I had said I had ended the lecture by saying that that calculation is has been done in the literature many times, I had pointed out to the appendix in Shikhar's paper where he has studied different approaches taken in the literature to do that calculation. But typically, the way that is done is to split this J or this J alpha into two components. We had discussed this yesterday. One of the components was photons from the continuum spectrum, and the other was these injected photons. Today we discussed what these are. And it turns out that the calculation is slightly different for JC and JR. You do it separately and then you combine the answer. And it turns out so I'll write down what the result is. To register the equation, it's a complicated equation, so don't expect it to make sense at immediately. But then we'll look at some plots where it will make more sense. So the solution for JC as a function of this quantity x, which I will define in a moment, is okay. So it's a, as you can see, it's a fairly complicated looking expression. It has three terms. There is this term, then there is this exponential term, and then there is this integral term. When we will plot it, it looks much simpler in a graph. So we will plot it. But the point to note here is this term roughly, this first term roughly, is kind of the naive bit. It's only accounting for the production of the JL by astrophysical sources, and then the remaining terms are quantifying the little distortion to the spectrum because of the absorption by the hydrogen atom. Okay. The detailed derivation of this is visible. First paper, I think, in a really nice way, but also in other papers. Okay. I should just maybe clarify this variable x is a famous dimensionless frequency variable, where mu 0 is the Lyman alpha frequency, so negative x is frequency is less than Lyman alpha, and delta nu is the Doppler width, which Thomas discussed in his this small a which appears is a void parameter. It's called a void parameter. It has the Einstein coefficient for Lyman alpha divided by 4 pi and Doppler parameter. And finally, there is an eta here as well. This eta is given by h by lambda alpha. This is called the recoil parameter. Okay. The alpha here is the Einstein coefficient, 6.25 times 10 to the 8. You can see how many orders of magnitude it is greater than the Einstein coefficient for 21 centimeters. And finally, I think the only remaining number that I have not described is this tau alpha, and that's the Gunn-Peterson optical depth, the Lyman alpha absorption optical depth. There are different ways this is written. This is one way. Here, this quantity gamma alpha related to the oscillators. Calligraphic F alpha is the oscillator set for Lyman alpha 0.4182. Anyway, so these numbers are just a way for me to evaluate this J3, but I should now write down the expression for Ji. Again, I will plot it. It looks simpler when we plot it. Sorry. Here. The expression for integration over y divided. Integration. It's just PLC rate minus infinity. Okay. So yeah, I think I'm not entirely sure how valuable it is to just write the equation. Just hold on. We will look at some of the plots when I get the screen down, and it's actually much more intuitive. I'm writing this down so that you become familiar with it, and then maybe when you look at the papers, it's a bit more useful. So Ji is just JC if X is negative. Okay? If the photons are red worlds, okay, smaller frequency than Lyman alpha, then Ji for those injected photons is just JC. And Ji is a different quantity. And again, here you see the same arrangement. It's a very different expression from what I had written for JC, but there is an undistorted term here and there is a distortion. This undistorted term will come from galaxies or sources of Lyman alpha, and then the distortion will handle the effects of the interaction. Okay, so I show just have some patience until we look at the plots. We look at them at the end, so that we have to bring down the projector only once. But the point is, once we have the expressions for JC and JI, we have achieved an important milestone. Namely, we now know J, right? Because that was just JC plus JI. So now, once we have J, we should start taking steps towards obtaining our X alpha and T alpha. So remember, what is J? It is the specific intensity, the same quantity that appears as I nu in our radiative transfer equations. Okay? Energy per unit area, per unit solid angle, per unit time, per unit frequency. It's the same quantity, this. And therefore, now, once I have the number of photons and the number of hydrogen atoms per unit volume, I can write the probability of their interaction. Right? So, rate of Lyman alpha scattering per hydrogen atom. This can now written as ER. Okay, and you can guess what this will be, right? It will have a J nu, but it will have to be multiplied by some line profile, some independence of the cross section. So there will be an integral of this form. So the atom doesn't just interact exactly at the Lyman alpha frequency, it has some non-zero probability of interacting at nearby frequencies. So that is this. And then there will be some atomic constant. This is this oscillator strength, calligraphic F. Yeah. So this P alpha now tells us we have taken one more step closer to getting our S alpha and T alpha, which is once we have J, we now know the probability per atom, that is where hydrogen number density here, of interaction with hydrogen. Sorry, m0 is the mass of mass of the hydrogen atom. Okay. Now, what was the quantity that occurred in, what do I need now to calculate the X alpha? I need the P10, the probability that this will lead to a de-excitation of my spin, the hyperfine spin states, right? So what I actually need is P10. Everyone remembers that P10 is what was in the expression for X alpha. So I need now to ask, if a hydrogen atom X interacts with a Lyman alpha photon, what is the probability that that interaction will lead to a spin flip to out of some field effect? The probability is not 100%. Not every interaction will lead to that. The probability is something less. It turns out that that probability is actually 4 by 27. Find this calculation in physics books. And so this P10 is actually 4 by 27 times TL. Now we have everything. The X alpha required your P10 star and T spin, right? So now I should be able to write down my expression for X alpha, the Lyman alpha coupling. But now what I have done is I have now, thanks to this calculation of J, incorporated the distortion, spectral distortion because interaction with hydrogen. So the expression can be written something like that. Here are some atomic constants, 27 times 321. So this is the expression for X alpha. It has your T star, has your T gamma. It has your J nu, which is the calculation we have done here, and it has a J alpha. I'm being a bit sloppy with my J alpha, unfortunately. But here the J alpha is the undistorted contribution, undistorted background of Lyman alpha. Just introduce J alpha here. And this is, if you look at the expression paper, this expression is usually written as S times J alpha by J0. This is how we will see it written in papers, where the S is this scattering correction. S is this integral here, J nu by J alpha by alpha integrated of frequency minus infinity. This is the scatter correction. Okay, and J, and then J0, this quantity J0 is the rest of it. This is 5.54 times 10 to the minus 8 times 1 plus z meter square per second per meter square. Okay, so you see what has happened? We get J alpha in our naive calculation. We have to divide that by J0 and multiply it by the scattering connection S, correction S, get the accurate J alpha. Okay. Now it turns out that I'll come to that too. So I hope it is possible for many of you to contrast this treatment of the Lyman alpha with what Kanan has discussed in his lecture. What I don't mean to say that what Kanan has discussed is wrong and should not be used in your calculation. Actually, that is what we do most of the times. What I want to emphasize is there are these important corrections which can be relevant if you are interested in certain quantities. It's very important to understand what Kanan has discussed, but there are these corrections which you should keep in mind. There is an expression which is actually derived by Shikhar for the first time for this quantity f. Write it down. Okay, where this quantity is a hypergeometric function. And this parameter xi1 is related to the numbers that go into there. In a certain approximate regime. It's called the mean approximation. So, for example, once you have, I'll show some plots, but if you have redshift of 22 and an electron fraction of 0 and a gas temperature of 10 kelvins, then your scattering correction is about 70%. Usually, number. Okay, so we have our X alpha. Now we need alpha. What eta? So the eta is the same eta that appeared in the expression for the recoil parameter. So what is T alpha? We need the T alpha and then our treatment is complete. This T alpha can be connected to the photon occupation number. Photon occupation distribution, which can be as once you have the specific intensity J of these photons, of these UV photons, that tells you everything you need to know about the photon occupation. You know how many photons are there at every energy. You can write this down as C square times J nu divided by 2 nu square. This J nu is what those expressions give. And this is N of nu. Then the T alpha can be obtained now as minus AB by H. Derivative of the logarithm of and nu computed at nu alpha. But now you see the effect is that this T alpha has been computed by using the distortion to the UV spectrum because of the interaction with the hydrogen atom. So when one plugs the expressions into these two formula, we actually get a T alpha that looks like this. We usually assume that the T alpha is equal to Tk, right? But what this expression is telling us is that that's not exactly correct. There are corrections to that, and the corrected expression looks like here. The quantity Tse is a small correction which looks like okay. This quantity Tse has a value of just 0.4 Kelvin, so it's a small. It's called SC because in exchange. So if TSE is very small, then you can indeed see that these TSE samples, and then you have P alpha approximately equal to Tk, which is the regime which we usually operate in. That is the assumption that Kanan made, and that is a reasonable assumption that we all make usually in our work. Okay. But the full expression for the spin temperature can be now written as we actually wrote down the full expression, but I can now write that down in terms of the TSE, and that looks like X Tk inverse X alpha This is exactly equivalent to yesterday's expression, but now we have replaced the T alpha terms with terms depending on Tk and Tsc, and we ignore Tsc. We get the usual equation which we assume. This is the expression that we normally use in our 21 centimeter modeling. Okay, so that finishes our basic modeling of the 21 centimeter signal. Okay, that finishes a complete treatment of all the terms that influence TS. Now, of course, we have to still take the remaining part of the journey is to connect the TS to the galaxy formation parameter, the physics parameter. I will come to that in a second. But before I discuss that, I want to highlight another complexity which emerges if you start to do this Lyman alpha physics activity. What is that? That is the effect of the Lyman alpha on Tk. So I have just told you that the Lyman alpha hydrogen scattering affects values of X alpha. So it turns out that it also affects the value of Tk. This is called Lyman alpha heating. So when a hydrogen atom interacts with a Lyman alpha photon, when it scatters a Lyman alpha photon, the atom either gains or loses energy, depending on whether what the Doppler motion velocities of the hydrogen atom was, and various probability factors, which were all included in the expressions for Ju. So essentially, both continuum photons and injected photons present around the hydrogen atom will constantly interact with the hydrogen atom, and every interaction will either take heat away from the hydrogen atom or add some heat to it. This effect also we normally ignore. It's the 10% effect to the gas temperature, and I will describe it. The basic picture is quite easy. The basic picture is the heat supplied by. I will start by writing down the expression for these continuum photons. Continuum photons is, you remember our factor Q in our thermal equation yesterday. So I will give a subscript C for continuum. Now this will be an integral d nu times h nu. H nu will be the energy available times this J alpha minus Jc. Here J alpha is the undistorted spectrum produced by the source, and Jc is the J alpha minus Jc is the photon taken away. So that amount of energy by conservation became the heat that was injected into the gas of the IGM. And again, you will have some numbers here. And now the idea is you have to put that complicated looking expression of Jc here, and then if you compute that integral, you will get an expression for the heat that is introduced by scattering of continuum photons with hydrogen atoms. I can write that down for you. So if you do that exercise, then you get the expression for Qc, and I'm dividing by 3 by 2 nkt. This was the form in which it appeared in the temperature equation yesterday. This comes out to be 8 pi by 3 h by kb lambda alpha J alpha delta mu v by nv. This is the Doppler width. This is the undistorted spectrum. The other numbers are reasonable. This is the hydrogen atom density multiplied by quantity called IC, where this IC is an integral over this. Okay, so this is usually positive. The continuum photons usually heat the gas up. Those numbers for which I sketch, this comes out to be of the orders of a few tens. And I can write down quickly a similar form for I, the injected photons, where this Jc will be replaced by Ji. You will now have 2Qi by the nk times the Hubble. Hubble is just because yesterday we wrote the temperature equation as the function of redshift rather than time. In the normal picture, stars and galaxies. I discussed this yesterday, right? The stars and galaxies will produce energies at a lot of wavelength as the black body that Thomas viewed this morning. Typically, the black body of a young star peaks at Lyman alpha each wavelength. They are very bright in Lyman alpha. And so, this is yesterday, right? Continuum photons is photons with energies between Lyman alpha and Lyman beta. The continuum of energy values that exist between the Lyman alpha energy and the Lyman beta energy. Any photon with energy between them. So photons will be present in the universe at all energy values. But photons with energies between these are particularly of interest because they will radiate smoothly as the universe expands across the line. They are called continuum photons. And we contrasted them yesterday from injected photons. Injected photons were higher Lyman series photons, which vanish. They get absorbed by hydrogen. Inside the hydrogen atom, they cascade down to Lyman. They become a Lyman alpha photon. So now we can write a similar equation for injected photons for I, and that has an expression 8 pi by 3 h by Tv lambda alpha. A alpha delta is the Doppler parameter, delta nu Doppler, and B times still have JC because on the negative side it was just JC. Remember the expression for JI. And on the positive side you have this. It's actually a very similar expression. You just a two contribution to this because of the expression that I wrote down. And now here actually sometimes these injected photons can cool. You will see when I show the plot immediately why that happens. But here this quantity can be negative because of these two terms depending on what dominates. So injected photons can actually cool the gas. Although the cooling is often subdominant to the heating because of containing photons. So we now have the total heating rate 2Q alpha by 3 ND. The undistorted spectrum J alpha is the IC. Then okay, let me just not write all the shape terms here, but then there are these terms. So at cosmic dawn is a major heating source, right? The major cooling source is the adiabatic cooling because of the Hubble cooling terms. There is no collisional heating or cooling at cosmic dawn. The number densities are too low for that. So then you have this Lyman alpha heating. And reionization hasn't started. Those X-ray sources that Kannan described haven't yet switched on. We are in that regime. And so there, this becomes actually the dominant heating source. Okay, so we started by writing this relationship, and then now we have described all the terms that go into the J, go into the spin temperature Ts, as coming from some cosmological terms, so involving the Hubble constant, Hubble parameter at redshift Z, or for example the various densities or velocities, or we have described them as depending on some astrophysical quantities which produce this Lyman alpha. Okay, I think it is important to register that this is now a complete picture of this. So this is where we start seeing the parameters of interest emerge. So for example, if you have some exotic model of the universe, the equations that it will affect are all written down. Okay. What we want to do now is, what I want to give you is a sense of two different ways this JNU can be modeled. Now, I think some of you have already done this, some of you have not done it, but this is now a classic problem in modern astrophysics cosmology, where you hit the problem of complexity. This JNU is describe a galaxy, right? But galaxy formation we don't know at cosmic level. We don't know which parameters describe galaxies. Is it 3 parameters? Which 3 parameters? Is it 10 parameters? Is it 100 parameters? We don't know that yet. So there are two approaches. Okay? There is an approach which is called often a parametric approach, where you say, well, I don't know exactly how many parameters are required to describe the complex astrophysics which creates JNU. But I would be very surprised if that astrophysics is dramatically different from what happens in today's universe. I will start from today's universe and construct a galaxy formation model that looks okay in today's universe. I may be wrong, but it's not a bad start. Okay. The other approach is actually what is called empirical. The empirical approach only works if you have real data. It doesn't work, which is why we don't have too much empirical approaches in 21 centimeter yet, because we don't have real data. But the idea behind empirical approach is I am not prejudiced. I keep an open mind. I don't know exactly how many parameters. I will try to avoid parameterization as much as I can, but I will add as many parameters as I require. I will not ask how many, what the physical interpretation of these parameters might be. I will just ask what the data is telling me in a very disciplined way. These are called empirical approach. Both parameters, both approaches have been very successful in galaxy formation over the years. After the first edges detection, empirical approach was for the first time available for 21 century. First time data was available. Okay, so I will now describe these two approaches of modeling JNU, and you will see, and then you can take that and make it as complicated as you want. I will try to describe something at a very simple level. This is something that Anna has treated very well in his lecture, so I will not take too much, spend too much time. But essentially, what we now need is, we want to know the UV emissivity of sources. This is the amount of UV photons they produce per unit volume every time, and this is just going to be number of UV photons per baryon times number of baryons in sources. This is a very crude model of galaxy formation. This is an example of a parametric model. You can now put parameters on this. I can say X number of baryon photons are produced per baryon, and so on. Okay. So in this picture, emissivity, UV emissivity as a function of energy at redshift Z is given by an expression that looks like this. This is the average mass of a baryon. This is the amount of stuff that is going into stars or your sources of UV, and this is the amount that the material that goes into stars produces in UV. Okay, and then what decides this? Won't go into the details because Kanan has discussed this. What decides quantity? What decides it? the details of the composition of the galaxy or stars, right? How many stars are there at what temperatures and masses? What is the property of those stars? Are they population 2, population 3? What kind of spectrum they possess? In other words, this is related to things like the initial mass function of stars and the SED of those stars, right? So you have numbers like, I think Canon must have discussed this, but for example, population 2 stars, you can compute from population synthesis models their SED, and you can find out how many Lyman alpha photons they produce per unit time and so on. What does this quantity relate to? What is the rho star dot? Is this dependent on? This is dependent on the cosmological process of forming galaxies, right? So what is the number of halos? I think this is also something that Canon discussed. You might have a minimum mass below which you don't form any galaxies. You might have a certain redshift at which you above which you cannot form galaxies, and so forth. So, for example, rho star dot in a very simple picture is usually written as some number f star times the Hubble h times a certain collapse fraction f whole by dz multiplying by minus 1 plus z, this is z and this is dt, and then rho bar. This is a simple model of calculating rho star. What this is, this equation is actually a galaxy formation model. Very crude one. Indeed, it will not match most of the observations of galaxies. You will want to modify this model. So it's a very simple and useful model because it connects in a very simple way something that is very complicated astrophysical quantity to something that is very simplistic and cosmological. It is a collapse factor. Okay. And everybody knows that this collapse fraction can be written in Press-Schechter type theory as certain critical density times the variance, the cosmological matter. Okay, so this is the excursion set theory. For those of you who know this, familiar. For those of you who don't know, you can read it up in a textbook. But the point here is quite simple. What you have in this expression on the right hand side is very simple cosmological quantity. Basically, the matter power spectrum. You have the matter power spectrum coming from perturbation theory in lambda cerium cosmology that is converting itself into this quantity F collapse, which is then converting itself into the quantity of star formation rate density. Once you have the star formation rate density, and once you have a hypothesis for how each star that has formed looks like, you can combine these two and produce your JNU. Okay, this is Canon has discussed this, so I'm going a bit fast. That is the logic. Now you can make this galaxy formation theory as sophisticated as you like. For example, if tomorrow some galaxy survey tells you something, tells you that somehow this equation is not correct, this has to be changed. This is where, and that sequence of dependence is how the change will propagate through the whole thing all the way to the 21st century. So this is the promise of that modeling connection we have been trying to develop in these lectures. Once we have this epsilon u, once you have this epsilon uv, you can write the equation for J alpha, the undistorted spectrum, which I believe Canon has written. As something like this. So you have a, this is the usual relationship between a flux and the emissivity. This is the volumetric emissivity, and you are asking in K9 dt, what fraction of photons go through a unit volume, and that gives you a flux. And so you have that epsilon UV, which you computed through this very simple galaxy formation model that goes into this expression and gives you this J alpha. This J alpha goes and sits into those solutions to the Fokker-Planck radiative transfer equation to get our distorted JC and JI, which gives us finally the brightness temperature. These Pn are the probabilities. I want to write this down. I think I'll discuss all this, but this Pn is the probabilities that higher ion is cascade. Now, one of the issues with this is that this integral is over redshift. Okay, so which means that this is essentially a line of sight integral, the one-dimensional integral. So I could actually generalize it to three dimensions. Three-dimensional. And the reason I would want to do a three-dimensional generalization is because now you have interferometric experiments at cosmic dawn. Hera is trying to look at the power spectrum at cosmic dawn. You have ARPAC, which is looking at the cosmic dawn. So for that, this expression will not do because there is no spatial dependence here. This is just a z dependence. This integral is over z prime alone. The spatial dependence has been integrated out in this epsilon UV. So a 3D generalization would look like something like, so firstly, it will now have a J alpha R Z. You have a 3D dependence on the position, and this will be 1 over 4 pi 1 plus z squared 0 to R max. Now, there will be a horizon within which all galaxies will contribute to my flux at where I am. Will be a d, this will be dr prime, there will be a d omega prime, and an epsilon uv r plus r prime. Here, the new prime is mu alpha 1 plus z prime divided by 1 plus z, where z is the redshift of the H atom, of the hydrogen atom that is doing the absorption, and z prime is the redshift of this. Okay, good. Can I have the slide? Okay, so I'll just quickly, in the last few minutes of my time here, I will just quickly show you some of the results of the calculation. So it gives you a feel of what's happening. So these are calculations done by Shikhar. So please do talk to him if you want some calculational details behind these. But these are solutions of those two terms, JC and JI. the continuum photon and injected photon. And this is shown relative to the unperturbed continuum, the unabsorbed continuum. So what's happening here, and the x-axis in both plots is this quantity x, the dimensionless frequency, nu minus nu naught by delta nu. Okay? So x equal to 0 is the Lyman alpha frequency. Those are the red photons relative to Lyman alpha. These are the blue photons relative to Lyman alpha. And now you can see what's happening here is that photons near the Lyman alpha frequency are getting reduced. Why? Because those are being absorbed by the hydrogen atom. This is the distortion that is coming to the background spectrum. And you'll see that this is offset. This minimum is not at x equal to 0. This is simply because the universe is expanding. So the photons that a hydrogen atom sees at Lyman alpha will actually be predominantly coming at higher energies in the spectrum around the hydrogen, such that they become Lyman alpha by the time they reach that. And this integral, the shaded region on this plot, is the energy which heats the hydrogen. So these are the amounts of photons which have vanished from the background. They were produced by the astrophysical sources, but they were taken up by hydrogen and they contributed into heat. In the case of GI, the plot looks very different. In the injected photon case, what happens is that you again have X on the horizontal axis and you don't have any blue photons now in the background. Why? Because in the injected case, you are injecting the photons at the Lyman alpha wavelength. So at the most, what will happen is these Lyman alpha wavelength photons will be absorbed and emitted by the hydrogen atom and they will redshift. So you will have red photons because they will be the redshifted injected photons available around the hydrogen contributed by neighboring hydrogen atoms, but there is no way you will have a blue injected photon. However, what will happen because of this Ji term is some of these photons will be absorbed and distributed into the high energy because of this Doppler curve. Okay, and so here you are seeing two shaded regions. This bit is the amount of hydrogen, amount of photons that have been taken out of the background by hydrogen atoms because of the interaction with the photons. So the unscattered background is a step function shown by the dashed black curve, and once the scattering happens, some of these red photons are absorbed and then they are contributed to the blue side. And then the blue side photons are going to cause a cooling of the hydrogen atom. So this is going to cause a heating term, and this is what is going to cause a cooling term. These guys are going to gain energy from the hydrogen atom and move to the blue side, and therefore they will extract energy out of the IgM. Here they will add energy by getting removed from the red side. Here is an example of what the standard galaxy formation picture that I described, where I connected the cosmological star formation rate density to the collapse fraction gives at very high positron-like redshift. Okay? So here again, what you do is you take the power spectrum of matter perturbations, you convert them into collapse fractions, as Kanan described. You convert the collapse fraction into stars, and then this is what you get for the rho star dot. What will you do with this? You will multiply this with properties of stars, the IMFs and so on, and then that will give you the J nu with the equations that we have discussed. Okay? And this is the result that you get for if you do that calculation. So let us first discuss the so the two plots show the kinetic temperature, the gas temperature as a function of redshift, and in this plot you see the global 21 centimeter signal delta T as a function of redshift, and the various colors show the stellar property, the amount of UV photons that stars will generate, which is a function of the IMF or various other properties of the stars. Here quantified as a number F. If alpha is high, then a given amount of stellar material will produce more Lyman alpha photons. If F alpha is small, it will produce less Lyman alpha photons. So this F alpha is varied from 0 to 100 here, and you can see that it has a significant effect on the global 21 centimeters. Moves it backwards and forwards. For the same F star dot, rho star dot that I showed on the previous. More importantly, you can see how it affects the temperature. The kinetic temperature would have just decreased, right, as 1 plus z squared without any, because of the adiabatic cooling, without any heating term, because the collisional heating doesn't work. And so what you have now is an effect of the Lyman alpha heating operating. Under extreme conditions where F alpha has very high values of 100 or so, you can see that the heating can actually heat. Just Lyman alpha photons can heat the gas above the CMB temperature. No X-ray heating. Sorry? It's not important. Okay. Okay, I'll just take one more minute to wrap up one comment on Lyman alpha. I said at the start of my lecture yesterday that actually some of these J alpha calculations are so complex that we are still understanding how to correctly compute. But I have sketched one computation for you here. I have basically written down all major equations from the literature. Now it turns out that the expression that I wrote for the flux J alpha created by the sources had a form J alpha equals an integral over epsilon alpha, right? Where epsilon was the volumetric emissivity of the stars and galaxies, and we just converted that into flux using the usual geometric conversion. Now it turns out that we are now slowly realizing that there is an additional complexity which we have missed here, which is that the J alpha that a hydrogen atom at a point sees is not the J alpha produced by all the galaxies around it. It is the J alpha that the hydrogen sees, which is reprocessed from, which is produced by the galaxies and then reprocessed by all hydrogen atom between me and the galaxy. So there is an attenuation term which further reduces J alpha until it reaches me from the source, which we have completely ignored. This is the attenuation term which we usually write in on radiative transfer as e to the minus tau. There will be an e to the minus tau to these Lyman alpha photons as well. This e to the minus tau will depend on whatever these Lyman alpha photons do by the time they get from the galaxy to the destination. Not a single mention of this e to the minus tau was done here. The reason is it's really hard. We've been trying to compute it in the last also. So in fact, Shikhar has produced some really heroic simulations of this using a beautiful technique which I have absolutely no time to describe, Monte Carlo technique of computing, in which what Shikhar does is create these cosmological simulations. This is a snapshot of a simulation at a cosmic dawn like redshift, where what is shown is this quantity 1 plus delta, the gas density, and you can see that there are little white circles. Some of you could see them. These are the locations of halos where we artificially insert sources of Lyman alpha photons, galaxies. Okay, this is our crude galaxy formation model that we can implant on this, and then we can calculate our J alpha. I have written down an expression of J alpha in the 3D, right? So I can use that 3D expression here. Once you do that, you get this map for the X alpha and this map for the TB, the T, what is written as T21 here. Okay, so you can see that there is a structure to this. That's at some point the X alpha is high, some point it's low. You can see that the correspondingly there is places where the 21 centimeter brightness is high and at some other point it is low. Okay, but this is the calculation that I have written down on the board today. What it misses is this e to the minus tau. We are still learning how to calculate the e to the minus tau. Shikhar will tell you in a much better way than me on the issues involved in that. But here is one attempt which we have recently made to compute this e to the minus tau. You can see the results change significantly. Okay, it's exactly the same galaxy, exactly the same star, exactly the same simulation box. The only new addition is now the attenuation term between the galaxies and the hydrogen atom. And you can see there is an agree that these maps look completely different. And this indeed has up to, I think, 40% or 50% change in the predictions for the 21 centimeters. So the reason I'm showing this to you is that the modeling of 21 centimeter signal is something that is still ongoing research. We're still learning how to do it. Not a closed problem. If some of you have ideas on how to do it, in fact, Shikhar and I have concerns about this result as well. We think that this can be improved in the future. This is not the end of the story. However, what we have shown in the discussion in today's lecture and the previous lecture is that we have finally connected things to cosmology and galaxy formation starting from the bright. What you could do now is if you have a brightness temperature measurements, you could do an inference and obtain insights on galaxy formation. Now, if I leave cosmic dawn and go to lower redshift, what will happen? These parameters will remain as they are, but there will be additional parameters thanks to reionization, something that doesn't exist at cosmic dawn. So if I move to the lower redshift universe, then we will have galaxy formation parameters, all of these parameters, plus reionization parameters. Then my modeling will be different. Then I will have to model galaxy formation plus reionization. So in tomorrow's lecture, we will see how that is done. And then hopefully all of you will